Welcome. So this week we are going into module 9, our penultimate module, or second to last one. We're going to get into what are known as congruence classes and modular arithmetic. Then our next module, which I will post next week, will be over our final concept, the Chinese remainder theorem, which actually is how to solve specific relationships in multiple congruence classes. So let's get into this. Today I'm going to talk about two specific things: congruence classes, and then secondly, linear congruence. So let's talk about congruence classes. First off, I'm going to tie all this kind of together. Throughout the class, a common and fundamental concept has been the question of divisibility. So as we talk about integers, we often ask, is A divisible by B? Well, this is not always possible. The answer sometimes is no. And so we have to have an idea of remainders, hence the division algorithm. Now, we also can tie this back into the idea of our Diophantine equation, AX plus BY equals C. Recall, when does this have a solution? Well, it has a solution. Another way to think about it is consider BY equals C minus AX. This has an integral solution. And some thinking about this divisibility comes in. This means that B divides C minus AX. Does that mean that B divides C or B divides AX? The answer to that is not necessarily. It doesn't have to divide both of them. However, we had a theorem that actually told us that the greatest common divisor of A and B must divide C. So there has to be something that divides B and A and C. So all of them must be divided by some common value. So this is the critical idea that we have in here. Now, congruence modulo, I'm going to come back and explain this a little more, but this idea, which denoted, I'm just going to note real quickly, is this symbol right here. You'll notice it's like a buffed up equal sign. It has three lines. Do not use an equal sign when you mean this congruence. And the second part of congruence, so we have two parts that we have to do. One is that little symbol. The second is we have to denote what mod we are talking about. So modular arithmetic is pretty much saying A and B have the same remainders when divided by, well, in this case, it would be divided by, that's typo, this should be n, congruent mod n. So whatever mod A is congruent to B mod n, if the remainder of A mod n, so if you take A and divide it by n, your remainder is the same thing as B when divided by n. All right, so a couple of important properties related to congruence. M is a positive integer. We don't generally consider negative modulos, but they do exist. We usually refer to them in terms of positive modulos, but we can. But if A is a positive, M is a positive integer, then these congruence classes are true. The reflexive property, if A is any integer, then A is congruent to itself, mod n. And that should be like a duh. The symmetric is that if A is congruent to B mod m, then B is congruent to A mod n, meaning they're both congruent to one another. The last one's actually an interesting one. If A is congruent to B and B is congruent to C, then A is congruent to C. Now, these properties kind of make up everything we're going to work on, and these give us the idea of congruence classes that we can then work on and give us the modular arithmetic. So just a quick note for any of you that do programming, in LaTeX, which is how I make my presentations, it's how I type up everything, my notes to you and so forth. I do /equiv and /pmodn. These are the notations I use that generate things. If you're using Python, you can actually literally compute these things very simply. In computer programming, modular computations are actually quite common. They can be used for a lot of different things. But in fact, I just saw a program the other day to do the Fibonacci sequence that has modular arithmetic in it. So, but we use a percent sign, B percent N means B mod N. So it's going to give you the exact same idea, but you don't have to do that if you don't want to. Also, we have negative values. So I'm just going to rewind 1 second. I defined A and B, notice in all these situations, to be any integers, not just negative integers, not just positive integers. So we can't have negative values. The way to think about negatives in this is the fact that a negative is less than a multiple of n. So -2 is 2 less than a multiple of whatever n we're dealing with. So 30 mod 4, 30, sorry, is, and I'm missing a negative here, is congruent to -4 mod 17, because 30 is 4 less than a multiple of 17, i.e. 34. So when we're dealing with our congruences, these are things we have to consider and understand. Now, this gives us an idea of something known as a congruence class. So I'm kind of going through this a little bit quick. Feel free to pause and go back over these things. We'll get to examples in a minute. But these are some basic definitions. And these are the foundations of what we deal with in this. In fact, a lot of number theory is based on congruences and congruence classes. And what are known as residues. We can go even, we'll get to in a minute. So there are multiple ways to represent numbers using congruences. We call each set of equivalences a congruence class. So let me show you. -4 is congruent to 1 mod 5, which is congruent to 6 mod 5, which is congruent to 11 mod 5, which is congruent to 16 mod 5. We can keep going on. We have 21, 26, etc. All of these values make up what's called the congruence class of 1 mod 5. Now, this is important because all of these are solutions. However, notice I denoted it with the value that was between 0 and 4. And this is where I'm going to get to in a second, as we get into what are called residues. So the complete set of residues is a set of integers such that every integer is congruent to exactly one integer in that set. So in the last situation, I'm just going to rewind and kind of point something out. I can't have a set that has both -4 and 1 if I'm talking about mod 5. It can only have one or the other, not both. So it has to have exactly 1, and a least positive integer for an integer A is the smallest positive integer B, such that A is congruent to B mod n. Now, what this means is all of the integers I'm looking for in my least positive residue, I'm going to underline that because that's kind of important. The least positive integers are going to go 0, 1, 2, up to n minus 1, because n and 0 are actually of the same, are actually congruent to each other, mod n. So we only deal with this set, which is the set from 0 to n minus 1. Now, for example, mod 5, a complete system of residues, is usually we use this 0 through 4 as I just denoted. But I could also use this one, -2, -1, 0, 1, 2. Or if I want to get really weird, I can go 0, 1, 2, 3, 19. Okay, that 19 doesn't really make a whole lot of sense, but you technically could do it. Again, there are reasons we do these things. Something like this modulo class, this complete set of residues over here, is actually a more common occurrence than you might think. Because what if I want to stay with 0 being essentially kind of my middle value and a little bit on each side? So there's different ways, again, we can approach this and deal with it depending on the situation. Now, that does not mean in the middle of the process we cannot utilize numbers outside of these residues, but we want to end up in a residue. Now, if any of you have taken abstract algebra, this should be familiar because this is the additive group Zn. And that's where this idea really comes from. All right, congruence arithmetic. By the way, if you've not taken abstract algebra, now you have a reason to take it. It will be offered next year. So congruence arithmetic. Well, If A, B, C, and D and N are all integers where N is bigger than 0, obviously we don't want mod 0, that's just weird. And A is congruent to B and B mod N, and C is congruent to D mod N, then A plus C is congruent to B plus D mod N. This is very, very useful. So that means that I can actually do addition and subtraction by simply using their congruences. But the last one's probably the most interesting because it actually means literally we can multiply and again operate congruences on anything. So I will do a lot of these examples, but this theorem is actually the crux of how all these examples work. Now, the first two, you can quickly note, follow directly from the definition of modular arithmetic. Because if the remainder of, if A and B have the same remainder divided by N, and C and D have the same remainder divided by N, then A plus C, their remainder will be the same as B plus D, give or take some multiple of N. So because it's plus or minus some multiple of N, it's actually going to be congruent to that same value mod N. They aren't exactly the same. They are within a multiple, and that's the key part. So let's consider the last one though. How would we prove that? And it kind of hints at all this. We can start by saying that A congruent to mod B is actually the same thing as A equals Kn plus B for some integer K. That's the definition. Similarly, C equals Ln plus D for some integer L. That's not a 1, that's an L. Now, that means that A times C, I can write it like this, multiply it all together. Now, notice real quickly, these right here, I can actually take them and I can factor out an N, which actually means that all of these, this part right here is congruent to 0 mod N. And this is my remainder. However, BD hypothetically could still be bigger than N. So it could be outside of our least positive residues. So we would have to take its mod N, but it would be with some multiple of that. All right, so that's the idea. So let's do some examples to help you see how all this works. So we want to find 18 mod 7. So I'm going to start with some simple examples of just how to find equivalence classes. Well, 18, and I notice I used an equal sign right here because 18 is equal to 14 plus 4, which is 2 times 7 plus 4. What this means is this part is going to be 0 and my remainder is just 4. So that tells us that 18 is congruent to 4 mod 7. All right, so with that in mind, can you find negative 88 mod 13? Go ahead and pause the video and try it yourself. All right, if you did it, a common thing that people do is they divide negative 88 by 13. However, the key thing is this is a negative. I actually said that negative 88 is equal to negative 91 plus 3 because we want a positive remainder. So because of that, I would have got, I end up with 3 is my remainder. So negative 88 is 3 mod 13. Now, if you did this differently, hypothetically, you may have come up with negative 88 equals negative 78 minus 10. In which case, negative 88 is congruent to negative 10 mod 13. But if you did this, notice this is not a least positive residue. So because negative 10 is equal to negative 13 plus 3, that actually tells us that this is congruent to 3 mod 13. So we always want the least positive residue to do this. All right, here's another one. What is 289 mod 17? Go. All right, so if you did that, you quickly actually notice that 289 is 17 squared, which means that the remainder is 0. So 289 is congruent to 0 mod 17. All right. So let's do another example. Let's this time use our arithmetic. So I have 13 minus 15. I want to know what that is mod 7. There are two ways in which we can do this. So I'm going to show you the two ways. Option one is what I refer to as the brute force method. I compute it all out and then I find mod 7. So in that case, I have 13 minus 15 is -2. -2 is equal to -7 plus 5. So that tells me that -2 is congruent to 5 mod 7, or in other words, my 13 minus 15 is congruent to 5 mod 7. Now, in this particular situation, that's not too bad, but that could get really, really hairy really quick, especially as we add more operations in here. There is an alternate way to do this. Let's start with 13 mod 7 and 15 mod 7. What are those? Pause the video and determine those two mods. All right, so if you did that, you would find that 13 is 6 mod 7 and 15 is 1 mod 7. What we can actually do now is 13 minus 15 mod 7 is equivalent to 6 minus 1 mod 7, which is then congruent to 5, because 6 minus 1 is 5. Hey, that was a lot easier. I didn't have to deal with negatives. My life is so much more beautiful. I love it. So this actually we can use to our advantage. We don't have to do that. It makes it so much easier. All right, so here's a different way. Here's a much more complex problem. 7 to the 13th power mod 10. Now, before any of you go scrambling for your calculators, I want you to stop. This problem, it seemed to be extremely hard to do without a calculator, but actually it's not. Let me show you. This is one of the ways where algebra, by the way, is going to come back and be useful. So first, we can note that 7 squared is 49. And 49 is 50 minus 1, so 7 squared is congruent to -1 mod 10. Okay, so that's kind of useful. That's kind of useful. What also that means, we can then say 7 to the 13th power is 7 to the 12th power times 7. I put the 1 just to be pedantic. But 7 to the 12th power is 7 squared to the 6th power, because we can again change the exponents using exponent rules. But we know that 7 squared is congruent to -1. So this is congruent to -1 to the 6th power times 7 mod 10, which is just 1, because -1 to the 6th power is 1, times 7, which is just 7. Sorry, that should be mod 10. That should be mod 10. So notice this actually was way easier than if I had to deal with this whole process by multiplying this out. Let's see how working. And this leads us to the idea of linear congruence. I'm actually going to stop the video and start a new one to help you, so this video is not a crazy one.